Again, I welcome you all to the fifth week of the live tutorial session for points and topology course. And today we'll discuss mostly question related to the product topology, box topology on the product spaces, and then some example related to quotient topology. Okay, so so let us begin with this problem, which is a like substantial problem in the note of this week. So so is it true that if you have a topological space X and Y is subspace of X with subspace topology, and A is any subset of X, then if I calculate the interior of A intersection Y inside Y with the subspace topology, whether that is always included in the interior of A from the original topology in X. So whether this is always satisfied or not. So any idea or guess at least? Anyone? Like just guess. So what do you think at least? Whether it is like true or false? At least that much. Do you have any guesses?
True, I think. Not sure.
Okay. So let's try to then prove if it is true. So let's just try blindly without going to, like, if it is not true, then I should look for an counter example, but just let's try to blindly try for it to prove. So for set inclusion, you start with an, suppose I start with an element with the left hand side. So interior of A intersection Y. So interior point of this set means there exists a neighborhood, open neighborhood around X, which is purely contained in A intersection Y. So this will imply there exists an in BD U, let's say that X content there, and such that this U is pure, like fully contained in A intersection Y. But this open U is inside the subspace topology of Y, right? So as U is, because this interior in the sense in the subspace topology of Y, so U is open in Y. So by subspace topology thing, that we must have, there exists some bigger set, say V, there exists V subset of X open in X, such that I can write U as V intersection Y, right? That's the exactly openness inside Y means. So that means you have actually this U. This implies actually your U that is now becomes V intersection Y, that is contained in A intersection Y, right? Okay, so now what I want to show that this X should lie in the interior of A. So I should get some neighborhood of X inside the small x inside capital X, such that neighborhood of X is purely contained in A. But from this thing I can't guarantee that this V is somehow contained in A or not. That I can't say from this thing. So apparently it is not sure whether it is possible, at least from this relation it is not like implied that X belongs to V contained in A. If we could say this, then that will imply that x belongs to interior of x a. Okay, but this step we can't say, because this might be a bigger set than a, but the intersection is contained inside this one, but not be inside this one. So we can't say that this is actually true, that this is a subset of this thing. So actually it is not true. And so like I have to think of some example where this intersection thing somehow is like this B set is somehow bigger than this A set. So that is kind of intuition. So there are many examples. I particularly thought of this one. So let us speak. So just not true. So for example, let x equal to just real line with the usual topology. That means which one induced from the distance function mod x modulus function, modulus distance function, and take y as just single point, because I want that set to be smaller. So I just, let's say, take 1, and a is one immediate immediate observation, that if a were open in x, then a intersection y is always already open by the subspace topology definition. So if a were open, then a intersection y also open. So interior is all of a intersection y, and a intersection y is always contained in a, right? Because a is open, so interior of a inside x is also a. So in that case, a intersection y is already contained in a. So so I should not consider any open set for my choice of a to produce the counter example, because for open a it is already true. Okay, so that's why I particularly choose a neither open nor closed type set. So particularly take this set 1 by n such that n belongs to natural number. So here 1, 2, 1 half, 1, 3, all those things are there. So this is not clearly open, also not closed, because it has the limit point 0, which does not belongs to this set. So a closure not equal to a itself, so that is not also closed, but that is not important anyway. But now if I calculate the a intersection y, that is just y itself, right? 1. And the subspace topology on y, it being a one single point, so the subspace topology on y is nothing but just the discrete topology or indiscrete topology, because there is only one point, so the topology consists of only phi and y. So this thing, interior of this thing, this is this set itself, because there is only one open set y and which contains y. So this trivially, if I interior of intersection y with respect to this subspace topology, if I calculate, then I will again get back this y itself, right? Because a intersection y is y, because those set y is already open in itself. So this is y, and that means this is 1. And on the other hand, the interior of this set with the usual topology of R is phi, because there is no interior point inside it, right? Because it does not contains any interval. If it is contains some open set, like for any point, if it contains a open interval, that means it will contains uncountable many points. That is like one argument. But in general also you can directly show that it cannot contain a whole interval, but this set is countable, but interval always contain uncountable many points. So this set A does not has any interior point. So interior of A with topology of X, this is empty. So clearly this cannot be, one cannot be subset of phi. Interior Y intersection Y, this is not contained in interior XA, right? So is this clear?
Yes.
Okay, so then let's go to the next one. So it is a bit of related to the like assignment problem, but not exactly. So particularly like it is also given in the in one of the exam exercise in the lecture note. So I just pick the first one. The second one is given as an subjective problem. Okay, so for this one you have already heard of this pseudo metric, where the like this D for metric D satisfies three property. First one is that dxy equal to 0 if and only if x equal to y. Second one is symmetry dxy equal to dyx, and third one is triangle inequality like dxz less equal to dxy plus dyz for all xyz belongs to your space is X. But in this case for pseudometric, the first condition is like omitted, that dxy equal to 0 not necessarily imply x equal to y. So there might points which x not equal to y, but still the distance dxy is 0. So for those points we pick, actually we can define a relation. So x is related to y in x if the distance between them is dxy is 0, right? So as it turns out that this is a equivalence relation. So once we have equivalence relation, so we have the set of equivalence classes, and they will form like partition, all of these things are equivalent. So anyway, but x tilde denotes all the equivalence classes. Now you have a map from x to x this hat, so just send your x to its corresponding class, and and that is a quotient function. So on the x tilde we define our topology such that this map is continuous, and this map is then becomes the quotient map or quotient function. So and on the topology on x tilde, that is actually also match with the topology that induced from this particular metric. We like modify the metric on x hat to get a metric on x hat itself. So that topology will actually match with this one. So the topology the metric on x hat defined as d hat of this distance between class of x and class of y is nothing but just calculate the dxy. So and this will be well defined. So if I pick like instead of the some other point, let's say x1, and here some y1, and x1 y1 are like x1 x2 are x and x1 related, y and y1 related, then even if I calculate the distance between x1 y1, that will be same as this one. So from that thing, this is actually well defined a well defined metric, and here the dxy equal to 0 d hat x, this x class y class equal to 0 if and only if the class are related, because that is exactly my this thing, because that will imply dxy equal to 0, hence x is related to y, that means their corresponding class are equal. So hence we get actually well defined metric on x hat, and once we get the metric on x hat, that we have the we generate the topology from this metric by the all open ball with respect to this metric. So the question is basically you check that the open ball, like even if D was not a metric, but we can still generate the topology by all the open ball, and that will give you a topology. So there, if I check the on XD, if I see an open ball, that will be an union of equivalence classes. So that means that will be some union of equivalence classes in this X set. So for that, what we need to show, so let's pick an open ball in XD. So let DRX, so it is by definition consist of all points in X such that the distance between XY is less than R. The open ball of radius R centered at X with the metric D. So now this open ball, yes.
So we can show that if any element is there in the ball, then
Yes.
its equivalence class will also belong to the ball.
Yes, exactly.
Then we can write this ball as the union of equivalence class.
Exactly. So that's what we need to show. Yes, exactly. So open ball in XD. So suppose a point belongs to here. So let Y belongs to BR dx. Then enough to show the whole class of this Y. This also this is all this contained in this BDRX. What is this? This as a set. This is a set, right? This consists of all Z in X such that Z is related to Y. So Z is related to Y means DZX is DZY is 0. So but so if I to show this one, suppose I pick a Z from X such that DZY is 0, then that will automatically imply that DZX is also 0 by triangle inequality, right? So if Z belongs to class of Y, then DZY is 0, and hence if I want to show that this Z belongs to here, so I have to calculate the distance between Z and X. So ZX, this is by triangle inequality, it is, I can write ZY because that information I know, plus DYX. But Y already belongs to this here, so distance between X and Y is less than R. So this is totally less than 0 plus R, which is R. So that means that is this Z belongs to this ball X. So for any Y, if it is in this ball, then whole class also lies inside this ball. So I can clearly write that BRD X, this as union over all Y belongs to this set and this equivalence class, because that is already content. So this is equals to class Y and union over all BRD X. So each open ball, this is a typical open ball in XD, so that I write as an union of the equivalence classes. So that's complete the first one. So for the second one, it is asked that hence the image of any open ball in X under Q is an open ball in X hat T hat. So that is almost clear, right? Because the what will be the image of this ball. So this is this map Q. So Q of this thing will be like this Q of Y, this class, but this class is already like already a one point. This is only one single goes to one single point. So if you just write that thing, it will be immediately clear. So second part, that Q of BRDX, this consists of like Q of Y such that Y belongs to BRDX, but Q of Y is this denotes the class, and this means dxy is less than r. Okay, but dxy is nothing but, again I can write this as, because by definition of d hat, this is same as, if I consider the class of distance d hat of class of x and class of y, this is by definition of d hat, this is dxy, and this is less than r. So this implies that it consists of all classes whose distance from x, class of x, is less than r. That means it is the ball of radius r with the metric d hat around the class x. Okay, so this is exactly the arcs thing, that image of any open ball under Q is an open ball. So this is the open ball. So it takes, Q takes the same radius open ball to same radius open ball to the one topology to the other. Okay, clear, right? So this also imply that you have this open ball forms a basis for your topology in both sides. So it takes basic open set to basic open set. So that also imply that Q is open map, right? Because to check the openness, it is enough to check on the basic open set. So on the basic open set, it is already satisfying that thing. So from there we have that Q is actually.
Will it imply continuity also?
Continuity, for the continuity, it is like you have to check the other thing, right? So if you take a ball here, then that inverse of that thing is whether that thing like is another ball, but that is also clear from here, right? They took the same ball to same ball.
Yes.
So that is also like implied, but just you have to write it separately in a like different manner, but the same almost same computation will give you the continuity also. Surjectiveness almost that is immediate. So also this is a quotient map also. Okay, so this is fine. So now let's go to the next one. So this is again a like problem in the exercise in the lecture note itself. So suppose you have a family of subset AJ in this XJ. So J runs over some indexing set, maybe countable, maybe uncountable, doesn't matter. So then on the product of this XJ, you can have two topology. Either you can give product topology. So product topology means you have all the projection map to be the smallest topology, such that the projection map all are continuous. That's the topology on the product of XJ. But also you can give another topology called this box topology. So which is again like in some sense finer, or like finer in most cases. So then the product topology, so where you consider all the open set of each xj and just take the product of all those open sets. So that will again form a base for a topology, and the topology generated by those basic open set give you another topology called box topology. So usually that is finer than the product topology. But now I have two cases. Suppose the collection of aj that I took, suppose that is closed in xj in either topology. Suppose if you work in product topology, then it is closed in that topology. Then what can you say about the corresponding product of aj, whether that is closed in this product thing? And then next is like, if you take the closure of the product of aj, whether that is same as the individual closure and then product. Okay, so in either topology, which of the thing are true, or at least for product topology it is asked to prove, so it will be true. So what happens in box topology? Because anyway this is finer, so it may not hold these two. So that's what about this question. So for the at least for the product topology, for the first part, anyone have any idea? So you need to show that this is closed, you need to show that the closure of this thing is this set itself, right? So that is one way. So like anything, like just product topology, if you follow the definition of product topology, I just said that the projection map in the product topology are by definition they are continuous. So just let me write that thing if that helps. So topology on the projection map I will call them by pj. So that is map from product of this xj to xj. Okay, map are continuous. Okay, so like if it is continuous, so can you write this product of aj as, suppose given aj is closed, so can you write this product of aj as intersection of this inverse of this pj of some closed set? That is the basic hint. So because continuous means it takes the inverse image of any closed set is closed, open set is open. So from there, can you see something? So any idea? What will be, suppose pj inverse of this aj, what will be the inverse image of this aj?
It will be, I think, product of all the like x1 times x2, but at the jth coordinate it will be aj.
Yes, exactly. So that will be the inverse. Now if you want the product exactly like product of aj, like can you get the intersection of this pj of aj? Just for think about two case. Suppose you want some a1 cross a2 you want, and you are saying that p1 inverse of a1 is this is a1 cross x2, right? And this p2 inverse of a2 is x1 cross a2. So what is a1 cross a2?
Their intersection.
Yes, exactly. So it is their intersection. So for all j, so this implies this pj inverse of aj is closed in this product xj for all j. Now you know that any arbitrary intersection of closed set is closed, right? That is by definition of topology. So if you take the intersection of all this pj inverse of aj over j, that is again closed. But this is exactly the product of aj, the same as like this one. It is like intersection of this thing, so it is ultimately like coordinate wise intersection. So ai is contained in xj, so whatever other in the other places it will always appear xj, so that will just be aj. So finally you get that is a just product of aj. So that completes this one, right? Given if aj is closed in this one, then this is also the product of aj is also closed in this product. Now like in product topology I said that this projection is continuous. So is the same true in box topology? In the box topology, does this function are still continuous?
Not necessarily.
Why?
I think it will be.
Yeah, it will be, right? Because like as I said already that box topology is finer than the product topology, right? There are already more basic open set than the basic open set of this one. So already whatever this is, whether it is strictly finer or not, but at least the topology generated by this product topology will be contained in the box topology.
Yeah. Correct. Yeah.
Yes, and if a map already is continuous in the like smaller topology, so if you put bigger topology already it will be continuous. So okay, so the exact will give you the same proof for even for box topology. Yeah, still pj's are continuous there. Okay, so now this holds even in box topology as well as product topology. So what happens in this case? If I calculate the closure of the product, whether that is equal to the product of the closure. So one direction is again almost follow not almost exactly follow from this argument, right? Because this what are this aj bar in any topology, the closure of a set is always closed. So if you consider the product of closed set, that by previous part it is closed in both topology. And if you recall the like other definition of the closure, so closure of a set is the smallest closed set that contains that set, right? Now this product of aj, each aj is contained in aj closure. So if I take the product of aj, that will again still contain in the product of aj closure. So I get a closed set that contains this set, and the closure of that set is the smallest set, so it has to contain in that closed set, right? So this containment is almost just follows from this thing, that product of closed set is closed. For the other direction, I have to particularly study in separate topology, but that will also again follow like similarly. Okay, so just let me write what I'm saying. So B as a closure is closed, so by A, product of aj closure is closed. Also this product of aj whole closure is the smallest closed set that contains product of aj, right? So all over this j contains aj, but aj is already contained in aj closure. Every set is contained in its closure for all j. So this implies that product of aj is also contained in product of aj closure. Okay, so being the smallest thing, so I have one closed set that contains this one, and this is the smallest thing, so it has to contain in this set. So this implies aj closure, this is also contained in j, this thing. Clear till this one? It is fine, right? And just followed the definition and use the part 1. Okay, now for the converse part, let's pick an element from this set. So for reverse inclusion, let so the elements will look like some sequence of sequence of points in this thing. So let me take that as xj. So each xj lies in the aj closure. That is an element of this product set. That is in particular xj belongs to aj closure for all j. So to show that this is contained in here, so if I pick any neighborhood around this one, now I follow the usual closure definition of this one. Okay, so what I need to show, if I take any neighborhood around this point, this product of this xj, so if that intersect this product of aj, then I will say that this point also lies in the closure, right? That is the usual definition of the closure, so I'll follow that one. So instead of taking any arbitrary neighborhood around this one, because it has the basic, it is enough to show that if I take any basic like basic open neighborhood around this point, if that intersect this for any basic open set, then that will also guarantee that it is true for any open set, right? Because the other thing will be union of this basic open set, and each basic open set that contains xj will intersect this aj, so hence the total union will also intersect. So enough to consider the basic open set, so a basic open neighborhood around this xj. So basic open neighborhood will look like some product of open set in this thing. So let uj over j, let open neighborhood of this xj. Okay, so now the topology comes into play. So here when I'm saying this is a basic open neighborhood for xj, so in product topology it means that except from the finitely many uj, all others uj should be equal to xj, right? Because the subbasic open set will be inverse image of this pj where aj is open, so uj is open. So except from finitely many uj, all others are equal to actually xj whole set. But in box topology, this uj can be any open set in xj, right? But that actually will not change the proof anyway, so just fix a basic open neighborhood in xj. I don't care whether that that uj is equal to xj or something smaller open set, that is xj, because by this is a neighborhood of this thing, so xj should lie in uj, and uj is open in xj. So whatever that thing, that would if it is xj, then xj is open in xj itself. So if it is smaller, then still it is open. The openness already, that is the important part to claim this one, right? So till this point I haven't said anything particular to product topology or box topology. Okay, now you know this xj lies in so this is a closure point of aj, and uj is open, xj belongs to that. So uj is an neighborhood of xj in capital xj, right? So by closure definition, again I should have that this uj will intersect aj at some point, right? So as uj is an open ONBD open neighborhood of xj, and xj belongs to aj closure, so uj intersect aj non-trivially, right? Now if you, so this is true for all j, right? This is true for all j. So if it is each of this uj intersect aj non-trivially, so if I even just take the product of them, that will again be non-trivial, right? So this is uj intersection aj, this product over j, this is also still non-trivial, not empty. Okay, so if it is non-empty, but what is this? This is nothing but just the product of uj and then intersect with the individual product of aj, and this is the required claim we want to get to. So this is a basic open neighborhood around this point, and that intersect this product of aj. So this implies that the point xj that belongs to the closure of the product of aj. So we started with a point in here, showed it here, so this set will also contain in the other one. Okay, so this implies product of aj closure is contained in the whole closure. Okay, so this is 2, so combining 1 2, right? So again the same thing, I will say that as in the proof I haven't used anything particular to the product or box topology, so the same thing will hold even in box topology. So so okay, so is this part is clear, or any confusion at any point? Fine to everyone? Okay, so then let's go to the next part. Yeah,
It's clear, but there's one general question that
yeah,
pops up.
so
This problem, the result is true in the case of box and product topology, both cases, right?
both cases.
So in one sense, it means that we are not getting any advantage of product topology, this example.
Yeah, so in this example you are not getting anything, but the thing is actually there is like the immediate thing that you actually tried that you sent actually in that direction, you can't prove it. Like sequentially it is not true. Like a sequence in the product topology is convergent if and only if the like individual sequences convergent. So the if and only part is not true in the box topology, it is true in product topology.
That if and only part, right?
Yeah, so that sequential convergent individual sequence part is not true in box topology. So in that way, that's why you can't prove like this thing for box topology. But in this argument, you can actually do that, and indeed it is true.
So that means there is that one regarding sequence. There is one place where we have an advantage for product topology. And the other advantage is it was shown by Sir in the class that we can have an advantage while constructing continuous functions if we have product topology in the codomain. So what other advantage do you think we can have by using product topology in place of box topology, other than these two advantages?
Okay, so I immediately don't have, but I think the same thing almost even if some other thing come like some other exam like advantage are there, but that will again come from in some like some composition or something of these two only. Like even the sequence thing also comes from that part only, that the if function is continuous if and only if the composition with each the projection map is continuous. So again even if you just get, because your topology is generated by those function only, like the continuity of those function only generate your topology, so whatever the difference will make or give you some good thing, so that will again come from something in terms of those only.
You mean the second advantage being that composition continuous?
Yeah,
right?
yeah.
Thank you.
Okay, so the next thing again is related to this co-induced and induced topology already done in class. So suppose you have a like space just as union of xi. On each xi you have a particular topology, let's say tau I, and then on x you put the co-induced topology from this collection. So just recall what is this co-induced topology. So you just consider the inclusion of each xi inside x, and on each xi you already know that is a topological space with the topology tau I. So just co-induced topology on x equal to this union is given by, so actually the co-induced comes from a collection of maps from a series of topological space to your this x, but in this case xi being already a subset of x, the map are actually the inclusion map. So let's say tau hat by this notation, so it is contents of all y subset of x such that the inverse image of all those inclusion are, so let's say the inclusion ji inverse of this y belongs to your the respective topology tau I, and this should be true for all I. Okay, where ji this is map from, okay sorry, this is not small tau, okay, tau I to your x, this is just the inclusion. Okay, so this being inclusion, so ji inverse of y just mean that y intersection xi, oh sorry, this is xi not x, xi, right? So this is nothing but all y subset of x such that y intersection xi that belongs to your topology tau I for all I. Okay, so this is the co-induced topology in this thing. So also okay, that is the other part, the covariant part. Okay, so now you can this restrict your this tau hat, this tau hat is a topology on x, and you can put now on each xi subspace topology induced from this tau hat, so denote that as small tau I. Okay, and now this tau I is the tau hat. Yes.
Sir, I always get confused between induced and co-induced topology. Is
Okay,
there?
yeah, so okay, just let me then say it. So in the induced thing, you have on the, like, you already have on the right side, you have topology. You have to want to put topology on the left side. Okay, so that is called induced topology. And when you have on the left side, you already have topological space, you want to put on the right side some topology, that is the dual of that thing, so that is called co-induced topology. So in this case, on the left hand side, each of this xi is already equipped with a topology tau I.
Okay.
So you, from those sets, so you want to make this, each of these inclusion map continuous.
Continue.
You want to put like the largest topology on X, which makes each of these inclusion map continuous. In the induced case, what do you actually take? If you had like this thing, like which is actually the product thing. So from the, like, suppose you had product thing J. So from these two, each xj, let's say again tau j, this you have projection map, right? So the
Yes.
induced topology on the this thing will give you the, like, product topology there.
Okay.
So here on the right side, you had the topology, you want to induce that topology on left side to make all the projection map continuous. And in this case, you have actually inclusion map, which you want to make like continuous, like putting largest topology, because smallest topology will always be there. So indiscrete topology, if you take,
Yes. And
then
that will
always, that will
definitely,
always continuous. Yes, so that's why you want
sir,
to put largest.
for induced and co-induced topology, or are these maps are also fixed, like inclusion and
No,
this
no, 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 no,
projection map?
no, no, no.
It can be any map.
It can be any map. Suppose if x, like x were not union of this xi, but xi tau I are any arbitrary set of topological space with some map, with
Okay.
some map is there, then you can
Okay.
always put a topology on X co-induced by these families,
Okay.
such that all these are continuous. Say similar for the induced thing also. Okay, so in this case we are only in the case of co-induced thing. So now tau I, these are like the, now again, so on the X you now get a topology, and xi are subset of X, so you can consider the subspace topology on this xi. So just restrict this to xi. So but if you just see in terms of this topology, what is this? This is intersect each open set of this topology with xi. So consider y intersection xi. Obviously this is now in xi, such that this y lies in tau hat. But y lies in tau hat, that means that y intersection xi belongs to tau I for all I, right? So this capital tau I, so don't confuse with the notation. I should have changed the notation. One is like the already given topology was capital tau I, and the subspace topology that I get from the co-induced topology, that is my small tau I, and that I'm considering in this case. So this tau y belongs to tau hat. Okay, but y belongs to tau hat, that automatically implies this condition. So this consists of all y intersection xi. So I'm not writing xi, it is already clear that it is will be inside xi. So such that y intersection, let me take as xj, because that will, so that belongs to this capital tau j for all j. Okay, so now on xi you have two topology. One is the small tau I, one is the given topology capital tau I. So asked to compare these two topology on any particular xi. Okay, so any guesses from the, at least from the structure, that one of them is contained in the other? Is it like somehow can you guess that one topology is containing the other?
In one topology, the sets are like Y only, such that Y intersection with Xi belongs to tau I.
Yes.
But in the other topology, elements are like Y intersection with Xi.
Right, but like one thing is you are already saying that Y intersection X, like these things are contained in already in topology. So in some sense that like set already comes from your the original bigger topology. So in some sense it seems that this topology is smaller, right?
Yes.
So that's the actually claim. So the small tau I is actually contained in the bigger this big tau I. So because that like sets already comes from sets of this capital tau I. So this is contained in capital tau I. Okay, so just group, let an element, let's say u belongs to small tau I. Now by definition, so then there exists y belongs to this capital tau hat. So basically so there exists y such that u equal to y intersection xi and y intersection xj belongs to tau j for all j. So from here can you conclude that u also belongs to tau I?
Yes.
Why?
Because now Y intersection Xi it belongs to Tj.
Yes,
so
exactly.
Y.
Yeah. So it is true for all j. So in particular for I it is true. So this implies u equal to y intersection x belongs to tau I. So maybe it seems small tau I as it is true for all j. So in particular I just put j to be I. So I get that I picked an element from this topology, I get an element in the bigger topology. Actually the other inclusion will not hold, as you can actually see. Okay, so for the B part, this tau hat is coherent with respect to this xi. So you need to show this one, but coherent with respect to this one means that a element is open in this u, let's say u in tau hat is u belongs to tau hat if and only if I intersect u with each xi that lies in this tau I, right? That the coherentness in this case, but that is almost clear from the this definition itself. So just a matter of writing. So to check tau hat is coherent with this xi small tau I, this collection to show u belongs to this tau hat if and only if u intersection xi belongs to this small tau I. Okay, for all I. That is the coherentness exactly. Okay, I'm just wrote the definition of the coherentness. Okay, so is it clear that why this will imply this one? One direction is like follows from this definition, right? So this direction, the opposite also clear, right? Because if it is intersect with always okay, no, like bit different is there because this don't confuse with the I this capital tau I and small tau I. So here this is lies in small the tau I. So take the forward part. Suppose u belongs to tau hat, so this means u intersection xi belongs to capital tau I for all I. Now if u intersection xi, this thing from this topology definition, this belongs to tau j for all j. From the definition of tau I know that u intersection xi belongs to this small tau I, right? This is for also for all I, because for whatever I choose, I already have this condition satisfied from this one. So
it will directly imply that u belongs to small tau I.
No, why u should belongs to small tau I? Because u is a subset of x, but tau I is a topology in xi.
U okay. Yes. It belongs to u intersection xi belongs to small tau I. Okay.
Yeah. So because that is the definition of these two lie in there. So this belongs to, so this direction is like follows from almost definition that this direction is also will follow. So if I start with u intersection xi belongs to small tau I for all I, then this will imply that capital xi belongs to capital tau I, let's say okay, tau j, let's say for all j, and for all I also, and for all I as well. But once you have this u intersection xi belongs to tau j, so this is belongs to tau I for all I. Just I took I equal to j. Yeah, true. So then only I can say u belongs to tau hat. Yeah. Hence this tau hat is coherent with tau I. Okay, so in general actually the point of this exercise also like the thing that this tau hat what you get, that may not be always coherent with the given this tau I, capital tau I. But if you induce, like you first co-induce the topology from the given this capital tau I, and then restrict your like take the subspace topology on each xi from this tau hat, then these two topology actually coherent. But this tau hat may not be directly coherent with the collection capital tau I. Okay, that is also like also Sad discussed in his note, you can follow there. Like this coherentness actually will not always true in general if you started with this tau I. but in the subspace, after taking this co-induced, then take the subspace, in that topology it is indeed coherent. Okay, so hope this is clear. Let's go to the next one. Okay, this
Before going to the next problem,
Tell me.
can you pull up the notes, please? The PDF notes.
Which note?
The PDF notes for this course.
Oh, okay. You want me to open that?
Yeah.
Okay.
Yeah.
Okay, just a minute.
And,
Can you tell me that, like, I have to share then other tabs, so just tell me which page number or where you have doubt.
Yeah. There is no page number here, but module 31, 2.7.
Okay.
And in the definition,
2.7.1.
Pardon?
Like first definition.
Yeah, 2.7.1.
Okay. Yeah.
So here the codomain space Y is fixed, right? For the collection to define induced topology.
Yeah.
So Y is it possible that Y can vary, like Y eta Y?
Yeah. Like in there is one theorem where sir exactly give the what is the collection there. Okay. Didn't it take different collection? The different collection will also work.
It should work, right?
Yeah.
It doesn't have to be fixed.
Yeah, it doesn't have to fix there. Yeah.
And can you pull up the next page? Yeah, the next page.
Yeah.
Because in the next page, 2.75, the xi's are not fixed. I mean, the x is not fixed.
Yeah.
So in the same vein, we can say that the
Y sure. So I didn't actually notice this one. Yeah, yi actually in general it is taken to be yi. You can take particularly y to be like y to be all yi to be y, but in general it is taken to be yi tau y. Yeah.
Can we? Yeah. Thank you.
Okay. Okay, so next go to this one. So it is like almost like a assignment question, if you can follow this one. Okay, so suppose you have X as topological space and A is any family of subset of X, and A is called point finite. Like this Krishna was asking that locally finite and point finite, this is two different notion, so don't confuse with that. So point finite means the collection actually for any point you have finitely many numbers such that A lies in finitely many numbers of there, so that is point finite. But locally finite you have to actually do with the topology. So for each point, for the locally finite thing, for each point you should get a neighborhood around that point such that the neighborhood intersect the family for finitely many numbers. And in this case actually you don't need the neighborhood, but just directly say that this family is point finite if that point lies in the finitely many members of the family. So this is actually different from locally finite for sure, because in this case you don't have to bother about any topology. Given any collection of subsets, you always have a like whether that subset is that collection is point finite or not. But to say locally finite, you have to have some topology. Okay, so suppose A is such point finite collection, and in particular let's take X to be R and the collection to be all singleton points over all this point belongs to all over R. Then A is clearly point finite because each element lies in exactly one set of this thing, so that is clearly point finite. And also closed because in the the complement of singleton set in R is open, right? So this is point finite family of closed subset in of the real number R. So now you need to determine the co-induced topology on X with respect to this family A, and then compare it with the locally finite collection of subsets. So if you follow the notes, actually for the locally finite if you have the locally finite collection of subsets and the topology co-induced by locally finite collection, that is actually coherent with the topology of this X. Okay, but in this case, as it will turn out that this is actually not coherent with the topology. Okay, so first thing first, so first determine the co-induced topology on X. So just as a go, can you guess what is the co-induced topology on R with respect to this family? Huh?
Oh, finite or discrete.
Okay, yeah, but in this case actually you will get discrete, because to show the discreteness it is enough to show that the singleton set are open, but singleton set are open here, because if you take any, let's say let's pick an element R only, then take any neighborhood like on the singleton R, the topology is discrete topology or indiscrete topology, there is only one topology there. So if you take the just singleton R and intersect with each singleton this let's say RS, then that is either phi or R itself. So in any case that is always like open in this collection, so that will be lie in your co-induced topology. Just follow from the definition, so nothing much thing, so just follow the definition of co-induced. So co-induced topology on X with respect to A is, let's say I'll again denote this by tau hat. So this is all Y subset of X, let in particular that is R, and this Y intersection with each of these collections, so this R, just like same as this thing, I'm not writing all this IJ inverse or dot that thing, but that is indeed the same intersection thing, so I'm directly writing this Y intersection R. This belongs to the topology of this set R, but that is the topology means that is contains only phi and singleton R. That is the only topology that induced from the topology of R, right? So this is for all R belongs to R. But for any subset of R, either R belongs to Y or R does not belongs to Y. So but in any case, whether the intersection will be phi or whole R. So this is always contained in this thing for all R. So this is actually consist of this is not a restriction at all. This is true for any subset. If you pick any subset of R, this condition is satisfies always. Right? Is this clear? Like if I pick any subset of R, then I intersect with some singleton set.
Sir, here co-induced topology, it does not mean the same thing which you just explained.
No, I just explained the co-induced topology only, right? Here also this is co-induced topology.
But we don't have any function with respect to we are trying to.
No, we have, right? Here also the co-induced family means here this R, this set R, this is included in R itself, capital R. This is the inclusion.
Include, okay.
So whenever you have this thing, so this is already a subset of like R. I have written as union of this singleton set R. R belongs to capital R. So this is the map. So the same thing, that's why I just said that this I'm not writing as this inverse of that thing, because that is ultimately y intersection xi. So
Yes.
in this case xi are my like x are my this singleton R. So now I am saying that this is actually the restriction that I have put this y subset of R such that this happens, but this is not a restriction at all. If you pick any subset of R, if you intersect with a singleton set, that is always will be either empty or the singleton set R itself, depending on R belongs to that subset or not. So this is not a restriction at all. So this is all subset of R. So this consists of all subset of R, as for any y subset R, y intersection R will be always like equal to phi if R does not belongs to y, or singleton R if belongs to. That's the only two possibility for anything for all R. So it lies in this set. So this consists of all subset of R. That means it is the power set of R. That means it is the discrete topology. Okay, so this is discrete topology. Now for part B, compare with the locally finite collection of subsets. So this is a locally finite collection. Now the topology that co-induced by this family, you get actually discrete topology on R. But on the R, the topology is not discrete, right? So that thing like, so this tau hat is not the usual topology on R, which induce topology on each of these singleton set R. That is, tau hat is not coherent. For example, just a singleton set, let's say if I take a singleton set is open here, and like singleton set R intersect with all of those things is phi or R, so that belongs to this tau hat, but the singleton set does not belongs to your original this usual topology. So this is not coherent. Even though this is a like closed collection of closed subset. So just go and check that actually in the locally, if you started with the locally finite collection of closed subset, then the topology induced by like co-induced topology induced by this co-induced by this family is actually coherent with the usual topology of the space X. Okay, so that's the like comparison.
Can you repeat that point? I missed it.
Okay. So I'm saying that instead of taking like point finite family, if you would have started with some locally finite family of closed subset, then the topology co-induced by that family is actually coherent with the topology of the space you started with, the topology that you started with on X. So
coherent with the locally finite collection.
Yeah. Sorry. Coherent with the locally finite collection.
So it works only for local finite,
Yeah.
not for point finite.
Yeah, point finite family, that will not work.
Achha.
So that is all about this thing. Okay, I can tell the particular page number also. Just let me check. Okay, it is remark 2.2.14. If you want to check, just
2.2.14.
Yeah, 2.2.14. Okay, so that is like all about this point finite thing. So in some sense, this point finite collection actually does not bother about the usual the topology that X had. So because by my choice of collection, it does not involve any topology thing, so it's natural to not have any connection with this coherentness also. Okay, so now go to the next one. So in this case, it is like, now it is about the quotient map. So suppose you have the projection map, you have two topological space x and y, and on x cross y you give the product topology, and now consider the projection map. So you have two thing x comma y, just send it to x. So whether that map is a quotient map or not. So just
Yes, sir. Yes, sir. It's a quotient map.
Yeah, why?
Sir, it is surjective. Because for every x I can, for any x I can find x y which is mapped onto x.
Yes.
It is also open, because any open set in x cross y, when I'll take its image, it will be mapped onto the open set in x.
Yeah.
And it is also continuous.
It is also continuous because I took the product topology, so already projection maps are continuous.
Yes, sir.
Yeah, true. So like that is again thing that open map or quotient map, right? Open continuous surjective map or quotient map. So like surjective continuous thing is fine, but openness actually imply the quotient map criteria that. Okay, just let me write the quotient map. So quotient map, the definition, if you just recall, so if from, I'm just again writing xy, just don't confuse with this xy, just if xy is quotient map, if I take any open set u in y is open if and only if f inverse u is open in x. So actually the topology actually, like in usual quotient thing, as we defined the topology on y, that actually induced from the topology on x. So then that such that this map is continuous. So that's exactly this quotient map thing is saying. So this is x is open. So all those elements in y is open whenever f inverse u is open in x. Okay, so one part is just the continuity thing. Okay, this is also surjective. A surjective map from x to y is quotient if and only if this condition satisfied. So u is open implies f inverse u is open, that is just the continuity. The other part is actually the mostly the quotient map part. Like f inverse u is open in x, then u has to be open in y. Okay, so for open maps, so just remark any open continuous or it may be not necessarily also open, even it is closed. So open or closed. Continuous surjective map is a quotient map. Okay, so it is almost easy to prove. Just if you given that f is surjective, so the almost just follow from f of f inverse u, this is always u. So suppose you are given f inverse u is open, the continuity part will imply this part, that u is open implies f inverse u is open from the continuity. For the converse part, if you are given f inverse u is open, then if it is open, then f of f inverse u is open, but as f is surjective, so f of f inverse u actually will be u, and that will imply that u is open. And similarly, if were closed, surjective, so this is a particular thing. And for closeness, if f were given closed, then you start with f inverse u is open, so the complement of that thing will be closed, and then f of f inverse, so just I'm writing f of f inverse, let's say a, okay, not a, u, let's say f inverse u, this complement, so this is a closed set, f of that thing will be closed, but f inverse u whole complement is same as f inverse of u complement. This is true for any, like, don't need any surjective thing or anything, so this is true. Now use the surjective thing, you will get u complement. So if this f inverse u is closed, so that will imply that u complement is closed, right? So u complement closed means u is open, so hence again this direction is implied. So in any case, just as this thing, just follow from these two relation only. Okay, so in this particular case, pi 1 is clearly x cross y to y is clearly surjective, first of all, continuous as on it is given product topology, continuous as x cross y has product topology, and also open, because the basic open set here look like either u cross y or x cross v, where u is open set in x or v is open set in y. So in either case you either get okay, sorry, I change it to y, sorry, to x. So when you project both of those set, always you get either x or some open subset of x. So in either case that is open, so hence it is open, and open as pi 1 of u cross v, which is a typical open set here. So in the finite product, you actually know that if you have the finite product, there the box topology and product topology both are same. Okay, so only in the not uncountable, in infinite thing only they are differ. So in this thing actually you can even check the basic open set are of the from u cross v, or u is open in x, v is open in y. Okay. So hence pi 1, similarly projection particularly onto the second coordinate will be again quotient. any projection to like any projection map from n many copy to any of that coordinate is again quotient map. Okay, so related to this one again, like immediate thing that just from the remark that any open or closed continuous surjective map is quotient map. So what about the converse? Is any quotient map is either open or closed? So continuous surjective is fine, that is implied as it is quotient map. So does any quotient map always open or closed? So that's what about the next question. So it is actually not true that any quotient map need not be always open or closed. So give example of maps such that quotient map x to y such that f is not open, and another case is f is not closed, and give one example where neither open nor closed. So in the first thing you can have f is closed, then it is obviously that is a quotient map just from the previous remark. Similarly in this case you give an example of an open map in particular such that that is not closed, and in the third case you give neither open nor closed. Okay, so any idea or guesses for this function?
Can we apply the idea that Sart taught us by using group action and the
yeah, you can apply, sure, but that thing I don't think immediately somehow follow. Okay, maybe that is an obviously an idea. You can apply group action and then that group action will give you a like quotient map, but that is not open or closed. That is a like bit, I think, bit tedious to check that whether that is an open map or closed map. If you like take your example bit nasty, that is not immediate. So again this is like example I just got it from book, so I just I'm writing. So I also like immediately I don't have exactly like construction of that thing, so I just kind of remember this thing, like frankly speaking. So in this for this one I just took particularly like you just so the idea basically is you take x such that where you have open set but that gets mapped to something closed set. So that's the idea, but if you want to consider this thing in real line, so the natural thing is the induced topology. You consider induced topology on disjoint union of two intervals 2 3. Okay, so you just send it to a like total closed interval. So you just shift this 2 3 interval to 1. So f gives that map. So you just take 1 2 0 2, sorry. So now send x to x if x belongs to 0 1, and x minus 1 if x belongs to 2 3. Okay, so clearly that gets on like surjectively onto this 0 2. Now this being disjoint union, so each of these set is open in this in the subspace topology of induced from R. Okay, because I can always take an open set, let's say like minus 1 comma 1.5 open interval. If I intersect that with this set, that will precisely give me this closed 0 1. So that means in the subspace topology this is also open and this set is also open. Correct? So these are open, but the image of this 2 3 under this map, it gets mapped to 1 2, right? Closed 1 2, and 1 2 in this subspace topology it is not closed, sorry, not open. Right? Is this clear what I'm saying?
Yeah.
Okay, so first that if is continuous is clear, because the only point like individually on 0 1 or 2 3 they are continuous. So I'm just pasting them and they have no intersection point, so continuous is like not at all a problem. They are actually bijective, like 0 1, this x is a bijective onto 0 1 and 2 3 is again bijective onto 1 2 through these two map. So f is anyway continuous and surjective. Surjective, and also it is closed, because if I take any closed set, that will again gets mapped to some closed set here, because this x sends any closed set to a closed set here. Similarly this also sends a closed set to here, but the only problem in the openness, because here you have point 2 and 1 which gets mapped to a closed point here, but here they are not a like what I say, they are also closed point, but they are also interior point in this set. So they are also interior point in this set, but where it gets mapped to, that is not an interior point. That's the only problem. So surjective as well as closed. So this implies f is quotient, but f of 2 3 is open, is 1 2, where 2 3 is open but not 1 2. Okay, so this is not open. Okay, the second example is a bit like easier to construct just from the previous thing. This pi 1 is already, this is a quotient map. Now can you find a like closed subset here, such that like in particular case just take x y both to be R. So can you find a closed subset in R cross R which gets mapped to open set? The closed set, I'll say that all label sets are closed. Label set, I mean like inverse image of some continuous function. So can you see some closed set of that form which gets projected to some open thing? So I'm saying this is actually the projection. Let's say R cross R to R is give you counter example. So this is not closed. But quotient so can you give me some closed set? There are many of them. So what about this picture?
Hyperbola, yes sir.
Yeah, so this actually takes, except the 0 point, the everything every point it takes like project down to, so only the 0 is the problem. So just
X into Y will take 1.
yes, one, yeah, one you take, maybe the other point is also okay, fine, right? 2,
Yes.
3 or anything you can take. So xy belongs to R such that x time y equal to c non-zero, let's say, or greater than 0 as my picture. So c greater than 0. Okay, just fix one c and take this set. This is closed because this is inverse image of the continuous function, like okay, this is closed. Can you say why this is closed?
xy is continuous function.
Yeah, so xy goes to x times y, that is a continuous function, so inverse image of a closed set is closed. So in this particular case I'm considering the singleton set C, so that is closed, so inverse image of that thing is exactly a C, so that's why it is closed. So is closed in this R2, but pi 1 of this AC, this is actually all of R except for the only point 0. So this is clearly open, right, not closed, because its complement is 0, which is closed, so it cannot be closed. So which is not closed. So instead of complement I should say that 0 is a limit point of this set, but 0 does not belong here, so it is not closed. Okay, so the example of neither open nor closed, so that is actually almost comes from this one, like the projection, but you have to restrict your function to a subspace. So I'm already running out of time, so I'll just give the thing, you just check, or I'll write and send the thing completely, but okay, you take A to be this 0 infinity cross all of R union all of R, so this is a one particular subset of R cross R, and this is cross 0. Okay, this is a subset of R cross R for sure, and you just restrict your projection map to this set. So I'm again saying this thing I haven't like created this example. These are you can find in any standard book or even in internet, so these are very standard, but I just wanted to like focus on this part, that don't confuse with the exactly, like it seems always like open closed map or quotient, so it need not be true that any quotient map is also comes from that. So there are enough quotient map which neither open nor closed, or open not closed, not open but closed, so that thing. So just to focus on these things, so these are already there in the, so I haven't created any of this, so these are already there. You can create yourself. Okay, so just restrict your pi 1 projection to R. Okay, this is again onto, because this coordinate you have R cross 0, so even just surjectiveness you get from this one. So is the restriction. Is the restriction of pi 1 r cross r to r. Okay. Fine. Now here actually you can again check that this is a quotient map. So another property of the checking quotient map is this thing. So again I'm just remarking that thing. Suppose if x to y is continuous surjective map, and gy to x continuous, such that if compose G, if compose G is okay, in which direction I want, x goes to x0, so on r y, yeah, if compose G is identity map on y, then actually f is quotient. Quotient map. So just use this thing. This is again easy to prove, just follows from the continuity and this part. It is already continuous surjective given, so now if it is given f inverse u is open, then you have to prove that u is open, but that comes from this relation that you take the whole inverse, so that will give you G inverse of f inverse u. If inverse u is open, G is continuous, so G inverse of f inverse u is open, but G f and G being identity, so that is exactly equal to u, hence u is open. So just easily just follow from that thing. So using this one, can you produce one function, let's say G from R to A, such that pi 1 compose G is identity on R. Can you give me some G?
X map to x0.
Yeah, exactly. So just take gx equal to x comma 0. So then clearly this is satisfied, and this is bit a thing that G is continuous, but that is also, if you just follow the inverse image. So if you take any open set here on R, okay, not on R, I have to check the continuity of this map G. So take an open set here and take the inverse, that will be exactly lie in this set R cross 0, but in R cross 0 it will be from the induced topology, that will be always open. Okay, so that is easy to check. Fine. And pi 1 compose, okay, this is first of all continuous, and pi 1 compose G is identity on R. So hence this will imply that pi 1 restricted on A, just I didn't put restriction here because anyway the domain is A, so whether it is just projection or restricted on A, that does not matter. So which quotient from the remark. Now you have to I'm saying that there are subset open here which does not map to open set here, and also closed set which does not map to closed here. Okay, so first it is not open. Can you see one open set which does not map to open set? So on this set it is R, right? So again the similar subsets will work in this, as in this case, because I restrict this my 0 infinity. So in the subspace thing, your like take your open set, let's say just which involve -2 2. So this open set cross what should I can take anything open, let's say 1 2. Okay, this intersected with A is an open set here, because in this set I already proved the subspace topology induced from this, and this is an -2 2 cross 1 2. This is an open set in R cross R. This is an open interval cross open interval, so this is open in A. But what is this? This intersection is -2 2. So as in this case 1 2, it does not include 0, so only the set intersect. It is 0 2 close this cross 1 2, right? Because it is from 0, so it will not be 0 here, so it does not include intersect this set, so totally lies here. So that's why I particularly took 1 2 this set open in A, but pi 1 of this set, so let's say this is my U, pi 1 restricted A U. This is just close 0 2 open 2, which is clearly not open in R, because 0 is not an interior point there. It's not open in R. So this is first. Second is again the previous example work in this case, right? The closed thing. Again this AC intersection A. Okay, just okay, AC my again is x comma y, such that xy equal to c greater than 0, closed in R2. So AC intersection A is closed in A. So here the thing is I'm considering, so if I just see this A in the plane, so this is the region, so on the positive x-axis thing, so this is in this direction, so all points include here, but also this R cross 0 is also there, so the whole x-axis, right? So this is your A, this is the A you had. So here if you just restrict your this AC, this parabola, so that is basically include this part only. So if you project down this, so it will include like open 0 infinity, right? Okay, but pi 1 A of AC intersection A, this is actually 0 infinity, which is clearly not closed, because 0 is again a limit point of this set, but not contained in this set, so not closed. R. Okay, fine. Okay, so two more thing actually. I'm already over time. So okay. So I'm just saying this. So suppose you have two quotient maps, whether the product of two quotient map is again a quotient map or not. So this is actually not true. This is false, and the example is not like easy to construct. So you can look for reference. Anyway, I'll write the solution and upload it in the drive, so you can also see from there. But actually the product of two quotient map need not be always quotient. Okay, so this is false. And last thing is like this is almost like a assignment problem. So you define your gx from r2 to r non-negative thing as xy goes to x square plus y square. Then this function you can show that this is a quotient map, and once you have a quotient map, then this g will define a partition of r2, right? Just take the inverse image of each particular point. So those will act as this map is onto, so that will define a partition of whole R2. Once you have a partition of a set, you can define a equivalence relation on that, and once you have equivalence relation, you can consider the equivalence class. So and that equivalence class will give you quotient space, right? So the quotient space, what is like what will be the quotient space? Actually you can check that the quotient space will be exactly this r greater equal to 0. That you actually don't have to calculate, but that is almost clear from this one, because you induce your, because g you started with, that is a quotient map, and you define the equivalence relation from that g only. So the equivalence class will also be equal to this target space y, because g is that g is the like space inducing this quotient space. So the quotient space will be exactly r non-negative. Okay, so these things are like just a routine check. The similar thing actually you can do for any some particular of this type of function. So the equivalence class is look like each circle, each one of this circle of different radius, that will give you a whole equivalence class. So let's say the radius is r, then this is x square plus y square equal to r, or you in particular can take r square, then this is r square, then all the element on this circle lie in one equivalence class. So that is exactly the inverse image of the inverse image of r square. Okay, so in this way actually you can do for any other particular function, whenever you have a quotient function from this, let's say r2 to in the target, if that is a quotient map, then the quotient space will be look like this one. Okay, so that's I all had to say. So if anything else anyone have to say, we can discuss, otherwise we will stop here. Any other question or anyone have?
Yeah.
Okay.
Can I go and have food? I'm hungry.
Sure. I'm also hungry too. Okay, like is it related to some assignment things or?
Pardon?
So is the like is it related to today's discussion or anything from assignment or this course note?
Which one? Question?
Yeah.
Yeah. Question means like I just want to have food. I'm hungry.
Okay. Then we may. Okay, we can.
Yeah. I mean, if anyone has any question, then please proceed.
Okay. Yeah. So do others have any question?
No, sir.
Okay. Okay, fine then. We'll meet next week.
Yes, sir.
Okay, so I'm stopping here. Bye everyone.
Bye.
Thank you, sir.
Yeah.